Welcome back to Physics 371 Online. Having defined polarization and explained a little bit about its origins at the atomic level, let's now look at something slightly more practical if we want to understand how a polarized object affects other objects around it. We are going to assume we have a polarized object and calculate the electric field it produces. So, to do this, one way to proceed is to find the electric potential that this polarized object has at a general point in space. From the potential, of course, we know how to calculate the field. So a polarized object can be regarded as a collection of many tiny dipoles. Remember that polarization is the dipole moment per unit volume. And so we can take an object that has a polarization, subdivide it into many small volume elements, each of which we can regard as having a tiny dipole moment. The collection of all of these dipole moments makes up the polarized object. So at a point in space, at a distance script r away from the element that contains the tiny dipole moment, we can write down the potential, the tiny contribution to the electric potential that that dipole produces. And we use the same formula that we derived for the case of a dipole itself. So this should be familiar to us from the end of Chapter 3. Now, dp, this infinitesimal dipole moment, can be related to the polarization vector by simply multiplying the polarization vector, polarization being dipole moment per unit volume, by the volume element d tau. So dimensionally, this works out just fine. So let's replace dp with p d tau and then integrate that contribution to the electric potential over the entire volume of the charge distribution. So here, the expression above, once we integrate it over the volume of the distribution, gives us the 1 over 4 pi epsilon 0 times the integral over the volume of p dot r hat over r squared times d tau. So we're going to rewrite this using an identity that allows us to rewrite the term r hat over r squared. And that's to remember that the gradient of 1 over r, this scalar function, is r hat over r squared. This was actually an identity that you proved in one of the very early homework problems of the semester. So remembering this identity, we're going to substitute that into the integrand to give us the following expression for the overall electric potential of the polarized object. Note that the integrand now contains a dot product. The dot product is of the polarization vector and the gradient of 1 over r. Alright, so we'll reproduce that on the next slide. And this is one of these derivations where someone clever had to know where they were going in order to come up with the following steps. Somebody must have had great intuition and used a bunch of vector identities and a little bit of vector calculus to derive the result that we're going to come up with here, because I certainly wouldn't have thought of it. So we're going to use an identity, or actually a product rule, from the front cover of the textbook that will allow us to write this integrand in slightly different form. So this is a case where we look at the divergence of the product of a vector function and a scalar function. P being the vector function, 1 over script r being the scalar function. And you can verify inside your textbook that this is given by the scalar function times the divergence of the vector function plus p dot the gradient of the scalar function. Alright, so then this product rule, if we look at it carefully, we see that the second term on the right hand side is exactly our integrand. Alright, so we'll solve for that term, the p dot gradient of 1 over r, and that gives us this expression. Note that there's a minus sign in here now because we solved for the second term on the right hand side, and this can be substituted directly into the integrand. So that gives us v is 1 over 4 pi epsilon 0 times the volume integral of this quantity del dot 1 over script r p d tau minus 1 over 4 pi epsilon 0 times another volume integral of 1 over r times the divergence of p d tau. All right. Now, one more thing we can do is to notice that the first term on the right-hand side is the divergence of a vector function, and it then can be rewritten using the divergence theorem. So remember, the divergence theorem says the integral of the divergence of some kind of function can be re-expressed as a surface integral, an integral over a closed surface of this function, the 1 over rp, dotted into the dA vector. So what we then can do is replace the first term on the right-hand side of the expression for v with this surface integral. All right. So what that gives from the expression in the middle of the slide all the way down to the bottom is an expression now for the electric potential that's composed of the sum of two terms, one being a surface integral and the other being a volume integral. Now, study these two terms for just a minute, and I think you'll see that they actually look a little bit familiar. For the first, in the first case, they actually have a very similar form. Ooh. What did I do? All right, here we go. They actually have a very similar form because they both have 1 over script r times something else, which is actually a scalar function. So what does that mean? You should have seen something like this before. Let me go to the next slide and just ask you to stare at it one more time and see if this looks familiar at all. Note that the first term has a surface integral, and it's got the 1 over script r. The second term has a volume integral, and it's got the 1 over script r. And if you don't see it yet, you're going to kick yourself when I reveal the next line, because each of these two terms looks very similar to the expression for the electric potential of a charge distribution, a special kind of charge distribution. Remember, when we were originally writing down the electric potential of a charge distribution, we found that depending on how the charge was distributed, this could be an integral over a line of charge, or an integral over a surface of charge, or an integral over a volume of charge. Now, what we want to focus on here is the surface and the volume terms. Because notice, this term, which represents the integral over the surface of sigma dA over script r, looks a lot like the first term in our expression for v. And the volume integral here is very, very similar to this term here. All we really have to do is make a couple of definitions to be able to equate these two terms. So this first term in v above looks just like the potential of a surface charge if we define p dot dA to be sigma dA. We just make that definition. And I'll call it sigma sub b for reasons that I'll explain in just a moment. For the second term, the one that has the volume integral, that one looks just like the expression for the potential of a three-dimensional charge density if we define del dot p to be equal to this rho, except there's a minus sign here. And so to be careful, we need to say that minus del dot p is equal to some kind of volume charge density. And once again, we put the subscript b on here. Now here's why. Because these are the so-called volume and surface bound charge densities. Why are they called bound charge densities? Well, that's because these charges are not really free to move throughout the object. They only arise because the object has been polarized. And so there's been a separation of charge that produces either a surface bound charge because of the separation of positive and negative charge within the material, and or a volume bound charge, which would be some kind of charge created within the volume of the material due to the polarization. So what we've got then is an expression for this sigma b. Note that from the definition up here, p dot dA equals sigma b dA, That is true if sigma b is equal to p dot n hat, where n hat is simply a unit vector along the direction perpendicular to the surface, the same direction that the vector dA has. So those two are completely compatible, and the second expression comes directly from the first one, just turned around. So with these charge densities defined, these effective charge density terms, we can substitute back into the expression for V and see that this electric potential produced by the polarized object is the sum of two terms. One of them is the potential of a surface charge, and the other one is the potential of a volume charge. So let's think about that for a minute. How can we use this to calculate V for a polarized object? And of course, let's remember that the goal is ultimately to calculate the electric field. So if we need to calculate V first, we will, but maybe there's a way of using this new information to calculate E directly. So let me just scroll back to that for a second. Look at the bottom here. How are we going to use this to find the electric field of the polarized object? And it's actually very, very simple. We're not even going to need to evaluate these terms for the potential, because what we'll do if we're given the polarization vector P, if we have an object, we know its shape, and we know that within that object there's this polarization, we can immediately calculate the bound charge densities because they both simply depend on P. We can calculate sigma sub b and we can calculate rho sub b. Of course, realize that sigma sub b is a surface bound charge, and if the object in question has more than one surface, it will have more than one of these terms. We will have to calculate a sigma b for each unique surface that the object has. Nevertheless, if we know the polarization, we can get these two directly. Then, the polarized object, for the purposes of doing this calculation, has become nothing more than an object that's got a charge within its volume and a charge on its surface. And if this object, especially if this object has high symmetry, and if the sigma b and the rho b distributions have high symmetry, we may be able to use our favorite tool, Gauss's law, to find the electric field produced by this polarized object. If we can do that, that will certainly be the easiest way to go. And so we'll be able to find an electric field due to the surface bound charge, then the electric field due to the volume bound charge using techniques that we've already talked about earlier in the course. And then, since the superposition principle holds, we simply add those two terms together to get the net field. Now this is a mouthful, and it won't really become very clear until we do some examples. But it's very beautiful. It's a very beautiful calculation that decomposes the problem of finding the field of a polarized object into simply finding the field due to the special kind of bound charge densities. And remember, bound simply means that these are not charges that we can move around by applying an electric potential. It's not that kind of charge. They only exist because the object has been polarized, and this is the effect that the polarization has on the overall charge distribution of the object, which was, of course, originally neutral. So we'll work on this in class, following these steps, and show just how powerful this formalism can be to find the electric field of a polarized object. I'll see you in class.